In this video, we're going to look at a couple of things. We're going to try to take two very different things and put them together to try to understand both the technology I'm going to be using, which is very old, and the mathematical methodology, which is even older, but which we use every day. In my fluid mechanics laboratory course, we talk about least squares and curve fitting. In the video, there's a link to that lecture, and there's also a link in the show notes to my little handout, which I'm going to be referring to as we go along. But in any event, least squares and curve fitting has been around a long time. Today we can do it with a spreadsheet with relative ease. The data input is easy, the output is easy, but one of the things I've discovered about spreadsheets and a lot of other tools is that, and it's something we've thought about for a long time, but we don't really tackle it very well, is the fact that people use stuff, even people like in engineering use things, and they really don't understand how it works under the hood. And one of the things I want to do with in my course is to give students some appreciation of what's going on when their spreadsheet magically produces this trend line that they want to use and they want to fit the data to. So with that in mind, let's take some steps backward. Now, in my course, I show them how and require them to do it by hand. And that's a little laborious for anything but very simple data sets. And in fact, I think some of them find it laborious for any data set. But we're going to just step up the automation just enough to be able to give you an appreciation for what's really going on under the hood in your spreadsheet or wherever you're doing your statistical analysis. And for this, I'm going to present this. This inside of here inside this case is a TI Business Analyst-I. And that means there was a 2 after it, and there was just a business analyst before it. It's a very simple calculator. It dates from the late 70s, early 1980s. The business analyst, I believe, was originally introduced in 1976. So it is an LED calculator, which means if you look very carefully, and I'll try to, we'll get a better view of this later, you'll see a little red number, a red 0, and that's what comes up when you turn it on. Now, that may seem delightfully primitive, and it really is, but there were good reasons in the late 70s to use LED calculators. Anybody who went through the era in the late 80s and the early 90s with the early LCD screens in computers will tell you that some of them were very hard to read and some of them on the calculators were very hard to read. And until they got really good backlighting that didn't run the battery dead in a few seconds, that really an LED was better. And there's also some things about, those of you who've been to sea know about, red lighting and whatnot at night. So, it's not a totally unreasonable thing to do. The numbers got bigger, obviously, with the later calculators, and that was always a good thing. But the business analyst is a fairly simple machine, and in fact, it shows you, I will show you the book for it. It's pretty small and compact, and I'm going to be using that book or screenshots of that book in the demonstration. And of course, books have been sort of something that has come and gone. In the early days of calculators, we had small books. And then we got programmable calculators, we got large books. Then we got computers, and we got some fairly substantial books. And then we got online help, and we got small books and lots of online help. Then we got no books and lots of online help. And so, these days, some of the stuff they come out with has got no books and not much kind of online help. So we've really kind of come full circle with that. But in any event, that being what it may, my objectives today are as follows. I'm going to show you least squares and curve fitting on this machine. This machine is capable of doing it. And the theory, as you can see over here, gives you an idea about what least squares and curve fitting is all about before the user plows into it. Now, anybody who knows least squares and curve fitting knows that the basic regression is linear, so that's why we call it linear regression. And our first example is going to be an example of linear regression where we take x and y and we try to attempt to fit a line that gives the best results. And like I said, if you want more details about that, you can look in my video on the subject. However, one of the interesting tricks, you may have noticed, don't know if you did, that right here are exponential and natural log functions. And those can be very useful in linear regression because we can actually plot equations other than straight up linear ones. We can plot power equations, we can do logarithmic equations obviously, and exponentials by doing some variable changes. And I discussed those in my monograph, least squares and curve fitting, in detail. I normally have not, at least up to now, required my students to do hand linear regression using those types of transformations. However, I'm going to show you how this is done. And the reason why I think it's interesting on the calculator is that you can actually see the data input and you can see the output. The input is a little complicated, but the calculator gives a fair amount of automation to the process, even though it's a little slow actually. But in any event, those are the two things. I'm going to use two sets of data. One set of data tends toward linear regression, and the other one can be going either exponential or power. And we're going to see which one is better. And actually, we're going to make a comparison with the data set that dates from the 1890s, where they actually did first. Because in the old days, actually, curve fitting was exactly what you plotted them on a graph, and then either using log-log, semi-log, or some other type of usually log-log or semi-log were the easy ways to do it. You could get to these exponential and power and logarithmic correlations. So with that, let's get into the calculator itself and show you how that works. We're going to take as our first case truly linear regression. We're going to actually attempt to find a line that fits a certain set of points. And how well they fit them depends on the nature of the points, and you're going to see that in this and the next example. The first one, the line equation, is to the left, and you can see it's simply y is equal to mx plus b. And that is our goal is given a set of x's and y's, we're going to find the slope and the intercept of a line for a certain data set. Now, the example that is given in the calculator's manual is one of them, and it actually shows you the sequence of operations to do this. We're going to use a different data set, but the sequence of operation is basically going to be the same. And basically what it amounts to is this. We're going to take a set of data points, and the graph you see there is from a Russian book I'm in the process of translating and putting up online on another one of my websites. However, first of all, the first thing I need to do is to take it off those graphs and put them on points. And now you see the data set that I'm working with. Now I'm going to show you how we're going to put the data set in. You'll notice here that we have two things. First of all, and this is the key right here where my finger is, X and Y are two different registers, and they don't necessarily correspond to the X and Y, but you can essentially create a two parallel columns of data using the X register and the Y register. And the other one is LR, which says linear regression. So if I tell the calculator I'm going to do linear regression, then linear regression is what's going to happen. So let's go ahead and look at that data set, and I'm going to input it. First, I put second, linear regression. The calculator knows that we're up and running. The first X value is 2.01, which you can see there. Then I do XY, and I put 0.067, and then I hit the sum. That's my first data point. Then I have 5.55 XY, 1.167, and then I hit the sum. I've got my second data point, 11.7, flip XY, and 4 there. And then 19.12 XY and 6.533, and then I hit that. That's my fourth data point. And my last one is 23.19, and then I flip it again, and I do 8.5, my last data point. Now, all my data points are entered. The two things I want to get out of this are the M, the slope, and the B, the y-intercept. So what I do is I hit second and M, and that's my slope. For what the y-intercept key, as you can is directly below it. So I do second and y-intercept, and I get that. Notice the slight delay in getting a result. That shows you the relative power of calculators then and calculators now. Now it would be an instantaneous, and with spreadsheets it is if the computer isn't busy updating or doing some of the background stuff that computers end up doing. So in any event, we're going to look at the next thing coming up is we're going to look at the a spreadsheet which gives a trend line. And that trend line, it shows that the values for the slope and the y-intercept, you compare them what's on the calculator, are in fact the same. So the calculator is able to do that. The calculator is also able, as you can saw from the instructions, is capable of actually taking the data you have just gotten the slope and y-intercept for, and by making an X input in an X, it'll give you a predicted Y either within the range, or outside the range. And one of the most dangerous things we do in engineering and a lot of other places is extrapolation, and that's it's not exactly extrapolation from a formal sense, but that's what it amounts to from an informal sense, and it can be very dangerous because the conditions within the range that you have may or may not exist outside of that range. May not. So that's something you have to be very careful of. So in any event, we have successfully done this, and you can see on a step-by-step basis how this works. Now let's turn to the next problem. And the next problem, to preface that, I'll show you the calculator's own instructions about how we actually can use linear linear least squares curve fitting to actually do nonlinear functions such as exponential functions, power functions, logarithmic functions. You can use those in those cases. And the two I'm going to concentrate on are power and exponential functions. And I'm going to use a data set. You see the chart, which is now on the left, and it looks pretty bad, but I think that has a lot to do with a lot of scanning and multi-generational reproduction. This comes from a paper that my great-granduncle James did in 1894, and it concerns the propulsive power of ships. And he was trying to establish some type of correlation or way of predicting the power that a ship would need to move through water at a certain speed. And the graph looks bad, although their ability to produce nice-looking charts and graphs is really something to behold, really, when they get it in its proper form, considering the tools that they had at the time. And we're going to show that we're going to see whether or not we can apply them and learn something. So let's start with we'll do like we do with the last one. We're going to transform the data set. And in fact, the paper that he presented gives this data set. I didn't have to use a piece of software to get it off with a graph like I did with the Russians. So we have speed in knots, that's our x-axis, and the horsepower for a certain ship, which is on the y-axis. And I'm going to try two correlations. The first one we're going to try is exponential. I'm going to turn to the equation for that, and I'm going to show something from my monograph on the subject. And you see that you have a y hat is equal to b hat e times mx. If I take the natural log of both sides, and by the way, one of the things about this calculator is that it only works in natural logs and exponents. So that was handy, and which is also, you could use common logarithms as well, although I think natural logarithms now are really much more preferred than common as they've been in the past. If you take that, you look at equation 23, it says it looks suspiciously like equation 1. Now, equation 1 is y is equal to mx plus b, which we saw at the beginning of the last demonstration. And if I do a change of variables, I can actually make it look like the linear equation if I change those variables. And the calculator allows you to do that on the fly. Before I put the data set back up, let's look at one more thing about about how to do this. You'll notice that we only do a logarithmic transformation of the y, and then in the reverse we have to do a logarithmic transformation of the b. Both of those are logarithmically transformed. So therefore, what we have to do is every y variable has to be entered taking its log. And at the end, the b variable we get out, you have to do the exponent to be the b in the equation 22. So let's proceed on that basis. So we start. First, we go into linear regression. Our x values are natural, which is fine. So we start with taking 8, and then we do that, and then we do 1050, and we take the logarithm of that. Notice it takes a little bit of time. We don't get ahead of it, and you can't get ahead of this, or this thing will throw a fit. And we do the same thing there, 10, and then we do 1600. We do the natural log of that, and then and that's the second one. Then we do 12, and we flip it. We do 2400. We take the natural log of that, and that's our third data. Then we do 14, and then 3800, and do the natural log of that, and that's the fourth one. And then we do 16, and we do that, and then we do 6050, take its natural logarithm, and we get that. We do 18, do that, and then 9420, take that natural logarithm, and we do that. And last but not least, 20, and then 13,920, take the natural log of that, and we do that. Now we have, let's see what the slope is. The slope is the same as, take the slope, we get that. And then we take the and the intercept, and then we take the exponential and the intercept to get it back to where it should be. And so that is the result for an exponential fit. Now let's continue with a power correlation, which we see on the left-hand side. Y bar is equal to B bar, X bar to the M power. We take the natural log of both sides of those. We see that log of Y bar is equal to log of B bar plus M times the log of X bar. So therefore, we have to take the log of both Y and X as we enter them, and of course take exponential of B coming out of it. So let's go ahead and get started here. All right, we're going to hit linear regression again, and we're here. So we start with 8, the natural log, flip the registers, which is 0, take that natural log, and I have the first data point. And then 10, take the natural log, flip the registers, and get 1600, take a natural log, and that's the second data point. And then 12, natural log, flip the registers, to 400, natural log, and that, okay? And then 14, natural log, flip the registers, 3800, natural log, do that, and then 16, natural log, flip the registers, and then 6050, natural log, and we have the fifth data point, and 18, natural log, do that, 9420, natural log again, there, and then 20, natural log, flip the registers, 13920, and we hit that natural log one more time, and we do that. Now we have all data points in. Let's recover. That is my M value, which is my coefficient. Now, and then I'll do my B value, which is that, but I have to take the exponential. So I do this, and that's what it is. And we're done. Now, I'm showing you now the horsepower versus speed from a spreadsheet. And if you go back in the video, you will see that the coefficients we come out with finally are actually pretty much the same as what the spreadsheet comes out with. Obviously, the spreadsheet's a lot quicker and graphs. And also, the spreadsheet additionally gives you a visual representation that shows that the exponential is the superior of the two correlations, even though in my great-great-uncle's original paper, he actually uses more of the power relationship for that purpose. So at this point, we are done with our demonstration. I actually require my students to do a truly linear by hand, but they could also do either or both of these by simply transforming the variables when you are going in, either one or both of them, going into the analysis, and then transforming the B value coming out of it. Now that I've shown you all the workings, just to recap, we had 3 different cases. First, a linear XY, y is equal to mx plus b correlation. Second, we had in exponential and power correlations, and for another data set. I hope that you have enjoyed this video and learned more about what's actually going on in your spreadsheet as you use these. So until the next video, thanks for watching and God bless.